Alright, welcome back. Today we are going to tackle how to draw Lewis diagrams. So I have this nice worksheet here, and I also put in this list of instructions. The first thing we're going to do is count all valence electrons for a molecule. We're going to draw the least electronegative atom in the center, draw single bonds to the central atom, then complete the octets with remaining electrons on the outer atoms first. So let's go ahead and check this out. Right here I have phosphorus trichloride. Phosphorus. Let's go to the periodic table. I'm going to draw how many valence electrons each group has. Phosphorus has 5. So I know phosphorus has 5 valence electrons. Chlorine has 7 because it is a halogen. Here's chlorine. But there's 3 of them. Times 3 equals 21 plus 5. So this molecule will have 26 valence electrons. Now I'm going to put the phosphorus in the middle because as you can see the phosphorus is less electronegative than the chlorine. So that just makes sense. Now I'm going to draw a single bond to each of the chlorines. I'm going to discuss in a different lesson how we draw these specifically because it kind of ties in with geometry, but don't worry about it right now. So these bonds count for 2 electrons. These are covalent bonds being shared by these atoms. So this is 1, 2 electrons that count for this chlorine. But these 1, 2 electrons also count for this phosphorus. So right now this phosphorus has 1, 2, 3, 4, 5, 6 valence electrons. Each chlorine only has 2. Now keep in mind it started with 26. So 1, 2, 3, 4, 5, 6. I already used 6 electrons. I'm down to 20. Now I'm just going to put electrons around these outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I'm down to 2. I got 2 left. Well, I already have an octet around each one of these atoms. I cannot put any more around these chlorines. But this phosphorus here only has 1, 2, 3, 4, 5, 6. So now I'm going to come in here and put a lone pair. That's what this is, a lone pair of electrons to fill the octet of this phosphorus. So if I count up each one of these atoms, they all have 8 valence electrons, and that is correct. Okay, we're going to have some more examples here, so don't worry. We have silicon tetrafluoride. So let's go count this up. Silicon. Silicon has 4 valence electrons. And the fluorines have 7. But keep in mind there's 4 of them. So that's going to be 28 plus 4. This will have 32. I'm going to put the silicon in the middle because it is less electronegative than the fluorine. Now, I'm going to draw a single bond to each fluorine first. That's 1, 2, 3, 4, 5, 6, 7, 8. That silicon's already good. So I have 24 left. And when in doubt, write it out. Just keep track of what you're doing over here so you don't get confused. So I have 24 electrons I need to distribute. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And that actually worked out very well for us. Everything has 8 valence electrons. The fluorine, 1, 2, 3, 4, 5, 6, 7, 8. So each fluorine has 8. The silicon has 2, 4, 6, 8. Everybody's happy, and that's what we're looking for. And moving on. Okay, here we have sulfur dichloride. Sulfur has 6 valence electrons. And these chlorines each have 7, but there's 2 of them. So we have 14 plus 6. This is going to have 20. And you want to know the secret. You want to know how to get good at chemistry. There is no secret. It's just practice. That's it. So here we have 20. We'll put the sulfur in the middle. Okay. Draw a line to our chlorines. 1, 2, 3, 4. Well, I'm down to 16. So let's go 1, 2, 3, 4, 5, 6. 1, 7, 8, 9, 10, 11, 12. Okay, well, now I have 4 more. These already have 8. But this sulfur only has 1, 2, 3, 4. So I'm going to have to put these lone pairs on this sulfur. There's nowhere else I can put these, and this makes it so this has 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's actually correct. Although it looks a little weird, that's correct. Alright, moving on. CHCl3. Okay, this is actually called chloroform. This is sort of one of those things where it has a common name that people always use. But let's check this out. We have a carbon, which has 4. Hydrogen, it has 1 valence electron. And of course the chlorines. That chlorine just likes to bond. It has 7 times 3. So we have 21, 22, 26. This whole thing's going to have 26. Now, what are we going to put in the middle? Okay, remember how I said put the least electronegative element in the middle? Well, you're probably going to think, what about hydrogen? It's 2.1. Carbon's 2.5. Here's the thing. Hydrogen never goes in the middle. Hydrogen only has a maximum of 2 valence electrons, which means it can only really bond one time with something. So that's never going to be in the middle. We're going to have to put the carbon in the middle. So we're going to go ahead and put the carbon in the middle. Draw our single bonds to these 3 chlorines. And also that hydrogen. Now once I do that, 2, 4, 6, 8. I'm already down to 18. Then we'll get into our Bob Ross mode and draw these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You're probably thinking, wait a minute, you didn't draw anything on this hydrogen. But this hydrogen already has 2 valence electrons. It can only hold 2. It only has 1 energy level, so that's already done. This carbon has 8. These chlorines have 8. So this chloroform is good. NH3. This is actually called ammonia. Not ammonium, that's NH4 plus 1. This is ammonia. But we have 3 hydrogens. That hydrogen equals 1, but there's 3 of them. And that nitrogen is going to equal 5. Oops. So we have 8. Yeah, like I said, you want to get good, make a whole bunch of videos like this. This is about the 3rd take on this video. So we'll see if I can get through it this time around without making mistakes. So we'll put that nitrogen in the middle. Now we'll go ahead and put those hydrogens. 1, 2, 3, 4, 5, 6. We got 2 left over, which we are going to have to put actually on this nitrogen. So that's a lone pair of electrons. That's what that's called, a lone pair on this central atom. And that is good. Alright, moving on. CH4. This is actually called methane. It's an organic compound, but we'll get into that later. We have hydrogen, 1 times 4. Carbon equals 4. So 4 plus 4 is 8, another 8. Put the carbon in the middle. Remember, the hydrogen cannot go in the middle. Do not put the hydrogen in the middle. We'll draw a single bond to all those hydrogens. And actually, check it out. That's it. It's 1, 2, 3, 4, 5, 6, 7, 8. So the carbon's happy. These hydrogens only get 2 each. And so methane is done. SiO2. All right, let's check this out. This is called silicon dioxide. Well, the oxygen has 6. Go check our periodic table. Here's the oxygen, it has 6. Always go to the wrong page. That's annoying. Times 2, 12. And the silicon equals 4. Yep, wrong page again. So 12 plus 4 is 16. Now the silicon is going to be in the middle because it's less electronegative. And we're going to go ahead and draw one covalent bond to these oxygen. So we're 1, 2, 3, 4. We're down to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now you're probably thinking, that's it. That looks great. We're done. Here's the problem. These oxygens are happy because they have 1, 2, 3, 4, 5, 6, 7, 8. They have a full octet. This silicon, not so much. It has 1, 2, 3, 4. It only has 4. So we don't have any more electrons to put on this. What do we do? Well, this is a great opportunity to show you what a double bond is. We just erase 2 of these, draw one more bond. Now check this out. 1, 2, 3, 4, 5, 6, 7, 8. That oxygen is happy. This silicon has 1, 2, 3, 4, 5, 6. Just erase 2 more. Draw a double bond. So now everybody is happy. That's what those double bonds are for. You could go up to a triple bond if you need to. So that's when you would use that. All right. I threw this in because this is confusing. Even for me, I had to look this up a little bit. This is called aluminum tribromide. And there's 2 reasons why this is confusing. The first is you're probably thinking, wait a minute. Last unit you said if there's a metal and a non-metal, it will form an ionic bond. But here we are talking about covalent bonds and drawing Lewis structures. And by the way, you cannot draw a Lewis structure of an ionic compound. These are all molecular compounds. So why is this here? Well, basically, it's all because of the difference in electronegativity. I'm not going to get into it here, but based on the difference in electronegativity between bromine and aluminum, it could actually sometimes form a molecular compound. So that's what we're looking at here, aluminum bromide. Now, I'm sorry, aluminum tribromide. So anyway, let's draw the Lewis structure. Aluminum has 3 valence electrons. These bromines have 7 times 3. So we got 21 plus 3, which would be 24. All right, let's put the aluminum in the middle, and we'll put these bromines out. So that's going to be 1, 2, 3, 4, 5, 6. We got 18 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now you're probably thinking, hey, wait a minute. A second ago you just said that if this central atom does not have 8 valence electrons, you need to draw a double bond. And this is actually why I put this in here. This is to illustrate the idea that there actually are some exceptions out there. Now, you're not going to get one of these exceptions on a test in high school because that would just be mean. But they are out there. So this aluminum actually only wants 6 valence electrons. It's actually happy right now. So we actually don't need to draw a covalent bond. So, unfortunately, chemistry has a lot of pirate code stuff going on. What that means is the pirate code are general guidelines, not set rules. Same thing with all of these, the octet rule or these Lewis structures. They're basically guidelines, but there's a lot of times when they are broken, when there are exceptions. This is one of them. Like I said, it won't be on a quiz or a test, but just understand that and know it for life. So then you won't graduate and say, wait a minute, my chemistry teacher in high school didn't tell me that there are all these exceptions. All right. Well, I'm going to stop here. Next time we're going to finish this up, and then we're going to go into polarity. So hopefully that will then help us understand molecular geometry. Thanks for listening, and as always, keep practicing.